All right, man. Welcome back to day 2 of 11.1. Let's look at example number 2. It says a geneticist claims that 4 species of fruit flies should appear in the ratio of 1 to 3 to 3 to 9. Suppose that a sample of 480 flies contains 25, 92, 68, and 295 flies of each species respectively. Find the chi-square statistic and probability. Okay, so first, I guess we should just make a chart with our observed counts. And there are 4 types of fruit flies. So we have 25, then we had 92, then we had 68, and then we had 295. Okay, so that was the observed counts. All right, and to calculate the expected, if you were to look at this ratio, we've got x plus 3x plus 3x plus 9x, and that should be equal to 480. So that means 16x equals 480. That's going to tell me what I should expect to have for each type of fruit fly. So when I do that, I get that x is equal to 30. So in this expected count for this total, because I had 1x, I would expect to get 30 fruit flies. And the next one, I should expect to get 90, and then 30 times 9 is 270. So now I guess if you want to carry on, we could find our chi-squared statistic for each one. So that is observed minus expected quantity squared divided by expected. So if I was to do that, 25 minus 30, square that and divide it by 30. And then I'm going to do 92 minus 90 squared divided by 90. We've got 68 minus 90, square that, divide that by 90. 295 minus 270, square that difference and divide it by 270. All right, so what I did, for each one of these, I got 0.833. For this one, I got 0.044. Third row, I got 5.378. And the last one, I got 2.315. So chi-squared in this problem is equal to 0.833 plus 0.044 plus 5.378 plus 2.315. So that gave me a chi-squared value of 8.57. So the probability that chi-squared is greater than 8.57, I'm just going to use the calculator. I had 4 categories, so the degrees of freedom is equal to 4 minus 1, which is 3. So that is equal to chi-squared CDF with lower bound 8.57, upper bound is 1 times 10 to the 99th, and degrees of freedom we should have 3. If you do that, you get a chi-squared value of our probability of 0.03559. So that probability would be less than 5%. All right, now we're going to go back. We're going to take a look at example 3. This time we're going to carry out another full-blown phantoms problem, but remember, because this is a chi-square procedure, we do not have a parameter of interest, so we're really technically going to follow phantoms. So example number 3 says the number of defects from a manufacturing process by day of the week are as follows. Monday had 36, Tuesday we had 23, Wednesday we had 26, Thursday we had 25, and Friday we had 40. The manufacturer is concerned that the number of defects is greater on Monday and Friday. Test at the 5% level of significance to claim that the proportion of defects is the same each day of the week. So I'm going to start off with H, and that is going to be the null hypothesis here, and I'm going to say the proportion of defects from a manufacturing process is the same. Monday through Friday. And the alternative, well, the proportion from a manufacturing process is not the same Monday through Friday. Well, what we have here is we have our observed number of defects. I need to look at the expected. Well, if we count all these defects up, 36 plus 23 plus 26 plus 25 plus 40, we have 150 total defects. So if I take 150 and I was to say, well, they happen equally, I divide that by 5, we should expect to have 30 defects a day. So we're going to put 30, 30, 30, 30, and 30. If this was an AP exam, you always have to make and show in your table that, yeah, you're going to have the expected number. You have observed expected numbers. So here we go. We need to look at our assumptions now. First thing we will take a look at is we are going to assume that the manufacturing process for this week was selected randomly. It doesn't mention that this was a random selection of 1 week throughout the manufacturing process. So I'm going to assume that the manufacturing process for this week was selected randomly. I will move with caution, or proceed with caution. Next, all expected counts are at least 5. So we're good. In terms of the expected counts, the simple random sample and my expected counts. And I'm going to say it was safe to assume there are more than 1,500 manufacturing mishaps. The name of the test is a chi-square goodness of fit test. T, I'm going to calculate my test statistic. So here, I'm just going to say that chi squared is equal to 36 minus 30 over 30 plus, and we're going to do 23 minus 30 quantity squared over 30 plus 26 minus 30 squared over 30 plus 25 minus 30 over 30. I got to square that. And lastly, it was 40 minus 30 quantity squared over 30. Looking at all of those, when you add them up, you should get 7.33, I believe it was. Pardon me, 7.533. All right, so we had 5 days, so the degrees of freedom is 5 minus 1, which is 4. So I'm going to obtain my p-value. So the probability that chi squared is greater than 7.533 is equal to, and I'm going to do this on the calculator, chi squared CDF lower 7.533 upper is 1 times 10 to the 99th. Degrees of freedom is 4. When I do that, I get 0.1102. So, making my decision, since P is greater than alpha, 0.1102 is greater than 0.05. And I forgot to write that up above. I'm sorry. I think we said 5%. So since P is greater than alpha, we will fail to reject the null. And then we do not have convincing evidence to claim the proportion of defects and I'm running out of room, so I'm just going to say it is not the same Monday through Friday. So that's that example. I could put this, I'll make a star so you guys could see it. I'll put that star and finish it up here. So to claim the proportion of defects from a manufacturing process is not the same Monday through Friday. That's it. So I hope you guys find this to be beneficial, and please check the agenda for your homework. If you have any questions, please don't hesitate to shoot me a discussion question. Have a great day, man.